Hi, this is Mrs. Cribb, and I'm going to be talking to you about the first chapter that we're going to be covering in class. It's called Chemistry for Life, and this is the notes for chapter 1 that's going to be covered in this Prezi. And if you look through these notes, I can give it to you as a hard copy or I can email it to you. But if you look through these notes, you can see there's really nothing to fill in. We're going to actually be able to talk about all of this through the Prezi. So I'm going to go straight to the Prezi now. Your Prezis are going to be basically a hub for all the information that you need for the chapter. It will include Quizlets and study stacks and different places you can go to help you practice the concepts. So here is Chemistry for Life, and I'm just making it full screen. The first section says Chemistry and Worldview. Chemistry is the study of matter and how it changes and the changes it undergoes. And we use chemistry to solve problems, cure illnesses, create fuels for rockets, to create plastics, polymers, all kinds of things. And we need to use the knowledge that we gain very wisely. Matter is anything that takes up space and has mass, or space is volume, and so has some kind of mass. And a worldview is a perspective from which to see and interpret all of life. It's how you think about things and how you start off looking at data. Your worldview is going to affect what you think when you look at data, look at experiments. So let's look at this first slide here. It just shows you the different kinds of matter that you might see, solids, liquids, and gases. Some of the solids like pencils and tables and apples, and the liquids, well, familiar with liquids, rain, drinks, and gases like air and wind. Wind is just moving gases. All of these things they take up some kind of space. They have some kind of mass. So they're all matter. Now I want to watch this video for a moment, and I want to pay attention to the worldview that you see here.
This is Sasha. This is Sam. When they first met, it was just small talk about where to find the best coffee, the new high top she just bought, a book of poetry he found at a used bookstore, a new local band she discovered just last weekend, a zombie apocalypse movie he saw last night with some friends from his martial arts class, her homemade screen print t-shirt, and his favorite Chinese restaurant, which made them both hungry. So they got 2 orders of Mandarin chicken with brown rice, and then Sam opened his fortune cookie. Life's journey ends with a new beginning.
Whoa, that's deep. But in the real world, life's journey ends with an ending. When you die, you're done.
Well, yes, your body no longer works, but your soul continues to exist, don't you think?
Your soul? No, I don't believe in ghosts. We're physical creatures, material objects, just a collection of highly organized atoms. When your brain flatlines, that's it. Game over.
So you don't believe in life after death?
No. I mean, it's a comforting thought, but there's just no scientific evidence for it. I'd rather face the real world than believe in a fairy tale.
Yeah, I agree with you, Sam. It's best to face reality. But it may be that life after death is reality. I mean, think about it. If life just ends at death, then everything we do or say comes to nothing. What meaning or purpose can our lives possibly have?
Well, I guess my life has whatever meaning I choose to give it. I personally believe in truth, beauty, science, making the world a better place, saving the environment, freedom of speech, and, tolerance.
Yes, that's all well and good. But what does all that matter if it ends in nothingness? What are your thoughts about God?
Which God? There are millions of gods.
The God that's in the Bible.
It's been proven that the Bible is just a bunch of mythology written by ancient desert nomads. But if faith in God makes you feel good, I won't argue with that. But I personally prefer more of a rational, open-minded approach to life. Here's what I believe, Sasha. You shouldn't think anything is true unless it's been scientifically proven.
But has that belief itself been scientifically proven? Sam, you and I look at life very differently.
Yeah, it's crazy. It's like we're from different worlds.
Not different worlds. Different worldviews. A worldview is the set of lenses through which you see the world around you. It's a web of habit-forming beliefs that helps you make sense of all your experiences. Through your worldview, you interpret life in a particular way. It affects how you think, how you feel, and how you live from day to day. To understand what your worldview is, think carefully about the big questions of life. Does God exist? How did everything begin? Who am I? Why am I here? Am I living a good life? What happens after I die? Cabbages and puppies don't think about this stuff, but people do. Reflecting on these questions is part of what makes us human. In fact, every one of us has a worldview. What's yours?
Okay, so we can see that worldview will affect everything you think about. Going back to this video, I don't want to play it again, but it's going to affect how you think about science. And I will say that some of the videos that we will watch in class will have a worldview where there is no God. But that doesn't mean that all of the data that's in that video you should just ignore. Sometimes there's really good data in there, and then they just go too far with what they're thinking. So we have to be able to determine that. We have to think clearly about that, and we're going to discuss it as we go along. Now, chemistry is also about modeling, putting models together. We are limited in what we can observe in the world, and so we simplify the things, but we deal with by leaving out some of the information and making models and looking at those models. A model is what we use to simplify the world in order to explain, describe, or represent it. So examples of models are computer simulations. We're going to actually look at one in a moment. A remote-controlled car is an example of a model. A globe is an example of a model. A model can be larger or smaller than the object they represent. Richard Feynman, a physicist and Nobel Prize winner, said, "What I cannot create, I do not understand." He also said, "Scientific knowledge is a body of statements of varying degrees of certainty, some most unsure, some nearly sure, but none absolutely certain." And so creating models helps us to know whether or not we truly understand something. Models are workable, they help us make sense of data, and they help us predict what's going to happen. And models are formed in part from the worldview of the creator of the model. Whoever makes the model helps you to, it's going to be reflected in the model. So you can have something like macroevolution and microevolution. And macroevolution is the larger evolution where you feel like that one thing evolves into a new species. And microevolution would be smaller in that one thing might slightly change depending on the environment, like dark skin and light skin, depending on what's going to protect you from the sun. Whether you believe in these two is going to be dependent upon your particular worldview. Now let's just look at some examples of some models. This first two models are a lot larger than the actual things. This is a model of an animal cell. See the nucleus and the endoplasmic reticula. It's larger. We can simplify it. Doesn't have all the nuances of a true cell, but it helps you to identify cells. And then we have Rutherford's nuclear model of an atom, which is not the latest model of an atom, but it still helps us to get a little idea of how an atom is put together. And this, of course, is a model of a solar system. And it shows you the sun and the relative sizes of the planets. And again, it just gives you an idea of how it's working. Now we're going to also look at a computer model right now. And when I have these links embedded into the Prezis, you just have to click on it and it should take you right to the site. Here it is. These interactive sites are great. So we're going to look at an atom, and we're going to create an atom. I'm using a computer model. I'm going to put some protons in the nucleus, and maybe a neutron in the nucleus, and an electron surrounding. And so I've created a model of the atom hydrogen. And I could actually look at it in different ways. I could put the electron cloud around the nucleus, or I could just show you the orbits, the main energy levels. And so this one has a lot of different things I could do, and I'm building a model to help us understand the atom. Oops, I didn't mean to make it small again. All right, so those are different types of models. Now, chemistry and history. Ancient chemistry. The Bible mentions that even as early as 5 generations after Cain, men began to work with metals. And early pharmacists that used medicines of sorts, some things that were kind of like medicines, were called apothecaries. You may have heard this term, apothecaries. The Greeks, and this is one of them, Aristotle over here, they philosophized and reasoned about nature. They never did any experiments. Basically, a lot of reasons. They thought you could think about stuff and just kind of figure it out, but also they didn't have the ability to do it. But they did come up with the idea of atoms, and that was a guy named Democritus who actually came up with that. So they did. They managed to think about some things that ended up panning out over time. Now later on, the alchemists came along and they went to the lab. Now we sometimes think of an alchemist as a shady guy who just wants to make gold, but they did a lot of things to contribute to science. They ended up making glassware and introduced a scientific method. So those were both major contributions to how we study science. And then some of the famous alchemists are Isaac Newton, Robert Boyle, and Francis Bacon. And I think I have another one over here on this slide. This is Robert Boyle, right there, that dude with the long hair. He proposed a definition of an element. We're going to be learning a little bit more about this later. But originally people thought elements were just earth, fire, water, and air. And I always think of the airbenders when I do that. But he changed that. So he said elements are substances that cannot be chemically decomposed or broken down into pieces. And then Antoine Laurent de Lavoisier, the father of modern chemistry, and you can see he's a French guy, he also was an alchemist. And these things right over here, this is just an example of some of the glassware that alchemists contributed to. Now, not some of these major new things, but using glassware to create and to be able to perform experiments were one of the major contributions of the alchemists. Now in modern chemistry, it started around the mid-1600s. The Renaissance era was going on, and the matter view began to be accepted, the fact that things were being made up out of little bits. And by 1800, chemistry became an actual academic discipline. And this guy here, Benjamin Rush, of the College of Philadelphia, was the first professor of chemistry in the United States, and he provided medications for Lewis and Clark, who took them on their exploration of the American West. This is a picture of this dude, Benjamin Rush, right there. And if you want to read an article about what he did, again, click on the link. Takes you straight to it. Now this is not mandatory, but it just shows you Dr. Rush's medicine chest, and watch, I scroll over it, hover over it, and you can just see all the different things he sent with them to help them, Lewis and Clark, on their expedition. So this is discovering Lewis and Clark and how he actually used chemistry to help them, to help solve a problem. Okay, now we're going to move on from there. 1b, this is the second part of the chapter 1. Why is chemistry important? One thing to remember is that chemistry is a tool that God gives us to solve problems. I was a chemist. I used to solve problems using chemistry by determining if something was contaminated. Way back when, I had to help this I don't know if he was a farmer or what, but determine if the pesticides were killing his chickens. And I'll tell you that story later, but it's pretty interesting. I got to do some fun things as an actual chemist. Chemistry reveals the complexity of creation, and that's one thing that's totally true, and makes you have it makes you see that the creator is even more complex, which is very different than what Carl Sagan believes. Chemistry and its applications can cure some disease, but it cannot cure death. Only Christ can conquer death. Remember that. Chemistry helps us. God gives us this tool to help us to improve our lives. But we can't prolong our lives indefinitely. We're going to die eventually. The only thing that can cure death long term, permanently, is Christ. And he just takes us into the afterlife where we can either live with the Lord or live where the Lord is not. So in hell. The command to create, loving my neighbor, and chemistry is in these next two sections. Now, when I say this, read these sections in your book to answer questions on your homework assignment. You may want to take a few notes. Occasionally, I may say something like this, and these are very, very short sections in your textbook. I can even look and see how long they are. It's like, oh gosh, 1, 2, 3, 4, 5, 6 paragraphs on pages 8 and 9. All I want you to do is just basically read through it, maybe write down a few things. You don't even have to, because you can, since the quiz is open note and open book, you can still look at your textbook. But I will not be, when this happens, I will not be testing you widely on this. On this particular one, I might ask you a question about something that's in there just because you can refer to it. But there's a couple of interesting things in here about Silent Spring and the use of pesticides that you might find interesting. But we're not going to cover that in depth, so I will leave that up to you. Next, we have rebuilding chemistry. All scientists approach their work with presuppositions or assumptions about the world based on their worldview. So we have a worldview, how we look at things, and that makes us assume something basically, and we are assuming things without any proof necessarily. So there's a naturalistic worldview that assumes that matter is all that exists, that human reason informed by science is the only reliable path to truth. This is Carl Sagan's worldview. I had to study this guy when I was in school. The cosmos is all that is or ever was or ever will be. Well, kind of put that in there. I would say God is what was before and will always be. The cosmos is not something that will always be. God will always be. So he kind of makes the cosmos his God. Naturalists, like Carl Sagan, have no creator or accountability. They have no moral code. All that doesn't mean they don't do good and bad, but they don't have it based on anything concrete. And they think that people are just chemical reactions or stardust. I've even read that a lot lately. They can't define good and evil concretely either. Although God does put within all of us a conscience that we write our own laws, and we all fail to follow those own laws, but we can't all define it equally. Concretely from something that we know is true. When science contradicts the Bible, it is not nature contradicting the Bible, but it is a scientist's model affected by his worldview that contradicts the Bible. I'm going to look at this one right here. I'm just going to scroll up and zoom in on there. Here we have two snowmen. Don't be absurd. Nobody made us. We evolved by chance from snowflakes. This would be a naturalistic worldview, something like this. Okay, so let's go back. When we study chemistry from a biblical worldview, we have the perspective that to expose error in science. Now this is this guy right here, that is Carl Sagan. He's mentioned in a textbook, and he is a very famous scientist. Read what he says here. How is it that hardly any major religion has looked at science and concluded this is better than we thought? The universe is much bigger than our prophets said, grander, more subtle, more elegant. Instead, they say, no, 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 my God is a little God, and I want him to stay that way. Well, see, that shows you just how he's looking at this from his point of view, his worldview. I don't see that at all. When I look at the complexity of an atom, when I look at protons and neutrons, electrons, quarks, when I look at the idea of string theory, which blows my mind, all I think is God created all this. My God is bigger than I thought. He's huge. He's more grand. He's more majestic. He's more powerful. And he put it all together, and I have to fall on my face and worship him. Carl Sagan couldn't see that because he wasn't saved. I mean, he was a godless man. What I see when I study creation more and more and more is I keep in mind, in the beginning, God put it all together, and everything we're going to study, all the order we're going to study, the complexity we're going to study, is just barely touching the surface of how complex the universe that our God made. Now, chemistry in action, observation and reasoning. In chemistry, in any science, we have different types of data. Quantitative has the quantity inside that word, and it means some amount, and so it has to have a unit, and it can be measured. So 10 kilograms, a number and a unit of some kind, a kilogram. 20 degrees Celsius, a number and a unit. 150 meters has a number and a unit. It has to be measurable. I could also say 60 seconds for a time, a number and a unit of time. So quantitative analysis is measurable. And then qualitative data just describes it with non-numerical data. It just kind of gives you a feel for what you're seeing. So it looks red. I could tell you something looks red. That would be qualitative. But I could also tell you the wavelength of light. That would be quantitative. That would be giving you a length and a dimension. So qualitative just kind of gives you something to describe it. Quantitative gives you actual measured values. Quantitative has to have a unit and some kind of number with it. Qualitative does not have a unit. Okay? Now, we're going to watch this little kind of lame video, but I like lame videos because sometimes they help you remember better than, nice, beautiful, complex looking ones. So just bear with me for a moment.
Qualitative, touch, taste, see, Quantitative, 1, 2, 3. Qualitative, qualitative, listen, smell. Quantitative, quantitative, measure well. Qualitative means you use your sense, that's right. Like hearing, taste, touch, smell, and sight. Quantitative means you use your tools, oh yes, to measure so you never have to guess. Qualitative, quantitative, senses and tools. Qualitative, quantitative, observation rules. One more time. Qualitative, qualitative, touch, taste, see. Quantitative, quantitative, 1, 2, 3. Qualitative, qualitative, listen, smell. Quantitative, quantitative, measure well. Qualitative means you use your sense, that's right. Like hearing, taste, touch, smell, and sight. Quantitative means you use your tools, oh yes, to measure so you never have to guess. Qualitative, quantitative, senses and tools. Qualitative, quantitative, observation rules.
Okay, so yeah, now you can see that was kind of a little bit silly, but it made me think about something too. If I described something to you as being light blue, what I thought is light blue and what you thought is light blue might be different. So that would be very subjective. So qualitative things are a little bit subjective, but quantitative are exact. I could tell you something weighs 1.2 grams and you could measure it out as 1.2 grams and we'd have the same exact amount of stuff. So one of them is more exact, one's more subjective. Now, deductive reasoning, it proceeds from a general statement to a specific statement. It proves the conclusions are true if all the premises are true. Scientists use this type of reasoning to make predictions. Example, all students like chemistry. Premise number 1. Abby is a student. Premise number 2. Therefore, Abby likes chemistry. Okay, this is deductive reasoning, and it would be true if Abby likes chemistry. So the only way that the conclusion, it would be true if all students likes chemistry. So the only way the conclusion Abby likes chemistry would be true is if both the first statement and the second statement was true. So this one was not necessarily true, but it is still deductive reasoning. And here's another one. All atoms have at least one proton. That is a true premise. Helium is an atom. That's also true. So therefore, helium has at least one proton. The premises are true, therefore the conclusion, therefore helium has at least one proton, has to be true. These are deductive reasoning, okay? They start from a general statement, all atoms have at least one proton, to get to something very specific. Helium has one proton. Inductive reasoning proceeds from known data to unknown general conclusions. So basically it goes the opposite direction. This kind of reasoning does not prove its conclusions to be completely certain. It can be wrong. I always think of it like this way. Inductive can be incorrect. And that's usually, even though I showed you that deductive reasoning can be incorrect if the premises are wrong, inductive reasoning is more likely to be incorrect. Scientists use this type of reasoning mainly for making theories. So it could be wrong. The theory could be wrong. Okay? Now let's look at a couple of slides. General principles. Using deductive reasoning, we go to specific things. Or if we take specific things and we use inductive reasoning, we go back to general. So general to specific is deductive. Specific to general is inductive. Remember, inductive can be incorrect. So here's some examples of deductive. All dogs are mammals. Premise 1, all mammals have kidneys. Premise 2, therefore all dogs have kidneys. This is very general to more specific. Dogs have kidneys. So here's a few more if you want to read. Here, since all men are mortal, premise number 1, Socrates is a man. Premise number 2, Socrates is mortal. So going from general to specific. Remember, deductive goes from general, all men are mortal, to Socrates is mortal, specific. Inductive, opposite. Socrates is a man, Socrates is mortal, therefore all men are mortal. So one goes from general to specific, one goes from specific to general. All right, now let's look at these two, and you might want to pause this for a moment and read through them and determine whether the following arguments are deductive or inductive. Okay, whoops. And so let me go back to that slide. There we go. And I'm going to give you a second. I want you to pause it, and after you think you've got it, then you can start it back up. All right, well, I'm assuming that you did that. So this example problem is actually on page 11 in your textbook. Number 1, when potassium chloride, sodium chloride, magnesium chloride, or calcium chloride, those are all different compounds, is mixed with water, it dissolves easily. Barium chloride is a similar salt. It also should dissolve in water. So we have these specific things: potassium chloride dissolves in water, sodium chloride, magnesium chloride, or calcium chloride. So therefore barium should dissolve. Well, this would be deductive because we're going from something very specific. I'm sorry, not deductive, inductive. We're going from something very specific to something more general, because we're taking a general the general conclusion about another molecule. These are specific things that are happening. Potassium does dissolve. Barium chloride is a similar salt. So we're going from specific salts to similar salts. So specific to more general, similar salts. So that is inductive. Now, letter B, any substance that floats on the top of water has a lower density than water. Vegetable oil floats on top of water, therefore vegetable oil is less dense than water. General, anything that floats on the top is less dense. That's a general thing. Vegetable oil floats on top, so it is less dense. This is deductive reasoning. All right, inductive, deductive. Hopefully you got those right. Now, the scientific method. First, we have the hypothesis, which is an educated guess or an educated explanation. This must be as simple as possible so that you can test it. If you make it complex, you can't really test it. An experiment is a way to observe a natural process, sometimes under controlled conditions, so a scientist can know, I just saw a typo, can know his hypothesis if his hypothesis is right or wrong. So that should be if. Controlled experiments have only one variable. Variables are factors that change. The independent variable is the thing that we're going to do the changing. I'm going to change something and then I'm going to see what happens because of it. And then, so the dependent variable is the thing that changes because of what I did. It's because of what the scientist did. Independent, the scientist changed. Dependent is what happens because of that. And then an experimental group is the group of samples exposed to the independent variable. The control group is the group of samples not exposed to the independent variable. So we're going to have a group we don't do anything to, and then we're going to have a group we do something to, and what we're going to do to them is change this independent variable. Empirical data is just the data you collect through doing this experiment. And so it's data a scientist observes or determines using the information gathered from the experiment. So there's a case study about, it's called Experiment in Orbit, and it is about flax seeds being grown in orbit and how the magnetic field, does the magnetic field on the Earth help plants know which way is up and which way is down? There's also the light, obviously, but if we apply a magnetic field to a seed, just like the Earth has a magnetic field, will it help the seeds know which way to grow? And so they did this, and this case study can be found on page 13 in your textbook if you'd like to read about it. And I will also show you that here's a NASA slide about that exact same experiment. Growing seeds in a magnetic field. So you can read all about it and see what happens. But basically they grew these flax seeds in a magnetic field out in space, and they have tiny little particles that are slightly magnetic and inside the seeds, and that they did see, or when they grew them, that they follow the magnetic field. And so that helped to show that applying a magnetic field to seeds will help them to figure out which way to grow, up or down. It helps them determine which way is up and down. So this was a scientific experiment rather, and where they controlled the experiment by applying the independent variable was the magnetic field, and the dependent variable would have been how they grew. Did they have a pattern? They had a control group that they didn't apply the magnetic field to, and they had an experimental group where they did apply the magnetic field. So if you want to read about it a little bit more in depth, check out this site. Otherwise, you're doing a little summary on your textbook on page 13. All right, and that brings us to the scientific method. There are many different versions of the scientific method and no standard form, and I say that because you can do some of these things in different orders, but generally you ask a question and then you try to come up with an answer for that question based on what you're looking at, your observations, and then you try to test it. Remember, the hypothesis has to be testable, And after you do the experiment, you analyze what you got and you form a conclusion. Was my hypothesis correct or not? I may have to go back and redo all of this. And so notice that this one has this kind of order, and this one says question, hypothesis, procedure, experiment, data analysis, conclusion, abstract, presentation. These are both scientific methods. Okay, some of them have just more steps than the others, but the scientific method is one of those things the alchemists help us get started on. Surveys are sometimes the only way to test a hypothesis is just to conduct a survey. A scientific survey is a process that involves randomly selecting representative samples from a larger population, and they rely on inductive reasoning. Okay, you could have, so this is just an example of a survey, and they did some kind of question, and it is a pie chart to represent the results. A peer review is when other scientists look carefully at what you've done, and that should always happen. Especially if you're doing something major. Scientists need to look at each other's work, and they have to make sure they're seeing what was actually done. That's one of those things we're going to talk about with our lab books and why we're going to use them and the way that we're going to use them in class. Because lab books become just like legal documents. Scientists need to be able to look at your data, look at your procedure, repeat what you've done, and come up with the same result, or find an error in what you've done. And if they can't, if they're able to repeat it, well, that makes it more and more believable, like something really happened. Theories are when scientists have tested some idea that consistently explains. So theories explain a certain phenomenon. Theories are scientific models. They prove their reliability when we can use them to make accurate predictions. So theories explain and make predictions. Scientific law is a statement that describes. So a scientific law describes what happens. A theory explains why it's happening. So a law is a recognizable repeating pattern in nature. It is based on observations made under many different conditions. Often these are mathematical. Generally, scientists consider laws to be very reliable statements of science that have no known contradictions. Newton's law of motion is an example, and the laws of thermodynamics as an example. Now I want you to look at this. Theories and laws kind of overlap. Theory explains. It's based on hypotheses. It can be used to make predictions and can be revised. Laws summarize, or laws they summarize a set of observations about a natural phenomenon. They do overlap, but they're not exactly the same thing. Here's one. The law of gravity is strictly enforced. Well, what's the law of gravity? Everything falls down. The Earth's gravity pulls us all down, and so that's been observed all the time. I have been a victim of the law of gravity myself. Okay, so that's the end of this first Prezi. I hope you are going to be okay with that. We're going to review and maybe do a couple of demonstrations in class, and I will see you soon.